Welcome to week number 6 of ECE 111, Introduction to ECE. In this lecture, we're going to look at topics that you cover in Math 165, Calculus 1, specifically differentiation using Matlab. So to see where Math 165 winds up in the ECE curriculum, this is the courses you need to graduate in electrical engineering. You start taking algebra, that's solving one equation, one unknown, trigonometry, the study of circles, sines and cosines. Then you get into Calc 1. With Calculus 1, you typically cover differentiation. Calculus 2 is you cover integration. So what is differentiation? Now, differentiation is finding the derivative of a function. That's the slope. That has a couple uses. With the slope, you can use that to find out what's happening at any given time. You can use it to find the maximum and a minimum of a function. For example, suppose I have this parabola. Think about it, this is I'm walking in a valley. The slope is the derivative. If I'm right here, the slope is the change in elevation over change of x. It's negative, I'm going down. Then it becomes flat, then going up. So again, the slope is telling you what's happening. One way to think about the derivative is think about your bank account. Suppose this is the balance in your bank account at any given time. The derivative, or the slope, tells you how much money you're adding or withdrawing. If you're adding money, the slope is positive. If you're withdrawing money, the slope is negative. So if I look at this, I can sit there and calculate the slope or the derivative. Initially, the slope is 0. The slope is change in y over change in x. So right here, the slope is 0, meaning I'm not adding money, I'm not taking any money out. The slope is 0. Between 2 and 3, my balance is going up. That means I'm adding money. The slope is change in y, which is 20. That's 20. Over change in x is 2. 20 over 2 is plus 10. So the derivative becomes plus 10 in this range. Then my bank account becomes steady. That means I'm not adding money, I'm not withdrawing money. Slope goes back down to 0. Between 5 and 6, I withdraw $20 in one day, so it becomes minus 20 over 1. Goes back to 0, then is increasing. The increase is plus $30 in 2 days. 30 over 2 is 15. Then goes back down to 0. So that's the derivative. The derivative is slope. And again, what the slope is telling you is what's happening with your bank account. When the slope is positive, I'm adding money. When it's negative, I'm withdrawing money. And the amplitude tells me how fast I'm adding or withdrawing money. So this is what the results should look like. Again, between 0 and 2, the slope is 0, plus 10, 0, minus 20, 0, plus 10, 0. And it's perfectly fine to have these jump discontinuities. Anytime I have a corner, the derivative is going to have a jump. Another application of derivatives. We've looked at global CO2 levels, and if you zoom in, this is what it looks like between 2018 and 2023. So the CO2 levels are going up, going down, going up, going down, going up, down. That's the total. Let's take the derivative. The derivative is the slope. What the slope or the derivative is going to show you is that when the derivative is positive, I'm adding CO2 to the atmosphere. When it's negative, I'm withdrawing CO2. And if you take the derivative, again, it's kind of like the slope, like right here. Take this guy right here, draw a straight line, extend it. It changes by 5, 10 over this time frame, over 0.8 years. If I were to take the derivative, here's what the derivative looks like. It goes positive, negative, positive, negative. And that actually kind of makes sense. If you look at it, this is January, when it's winter in the northern hemisphere. Well, most of the landmass on the Earth is in the northern hemisphere. So that's where most of the trees are. When it's winter in the northern hemisphere, CO2 levels go up. That's because the trees are dropping their leaves, the leaves are decaying, releasing CO2. In the summer, the CO2 levels are dropping. That's because in the spring, the trees put out leaves, they absorb CO2, trees are undergoing photosynthesis. Peak is in July, not surprisingly, turning sunlight and CO2 into sugars, and then it goes back up. So again, the derivative is telling you what's happening. In addition, there's kind of a hiccup right here. That's right around January, February, March. Right around March, on most years, there's kind of a hiccup. I'm not really sure what's happening, but that's what the data says. That's what's happening to the global CO2 levels in March. Again, the fact that I can't explain it doesn't mean it's not happening. So that's kind of what a derivative is. Derivative is slope. And with a slope, you can tell what's happening to a function or whatever your data is. Now in this lecture, what we're going to look at is how to find the derivative. That's something that you cover in Math 165, Calculus 1. We're going to find the derivative using lookup tables. That's kind of what you do in Math 165. We'll find derivatives using graphical methods and find derivatives using numerical methods, i.e. Matlab. And then we're going to use that to evaluate different paths for a robotic arm. Again, with a robotic arm, I might have like a two-link arm right here going from point A to point B. There's different ways to do it. If I look at the angles, that's the angle of the motor. The first derivative is the velocity of the motor. Velocity is roughly voltage for a DC motor. If I look at the second derivative, that's acceleration. Acceleration is current for a DC motor. And different paths result in different implied voltages and currents. Using derivatives, I can see what a given path implies in terms of voltages and currents by looking at the derivatives. So that's where we're heading. Now, the first approach that used in Math 165, Calculus 1, uses a set of rules. The nice thing about derivatives is if you have a function, just apply a rule and you get the answer. For example, if I have x to the n, the derivative is n, x to the n minus 1. That's just something that you memorize. The derivative of an exponential, e to the ax, is a, e to the ax. Again, something you memorize. Derivative of sine of ax is a cosine of ax. Derivative of cosine is minus sine. There's the chain rule. If I have the derivative of two functions, it's the derivative of the first times the second plus the first times the derivative of the second. And for division, I get this one. And kind of one way to memorize it is ho d high minus high d ho over ho ho. That's kind of the way I memorized it. Ho d high minus high d ho over ho ho. Bottom times the derivative of the top minus top derivative of the bottom over bottom squared. So that's kind of a set of rules that you learn in Calculus 1. With those rules, I can do things like find the derivative of cosine of x over x squared plus 1. Now, when you get to Calc 1, you'll do it using these memorization, these tables. In this class, we're going to be using Matlab and graphical methods. So suppose I have this function right here, y equals x squared. Find the derivative of y equals x squared. And to do that using graphical methods, I'm going to pick a couple points, like right here. If I pick this point, draw the tangent to that curve, and then the derivative is change in y over change in x. That's the slope at this point. And as I move along, the slope changes. So again, if I do it at the first point, looks like the change in y is about 0.51, 1.5, about 1.7. Change in x is 246, so it's about 1.7 over 0.6, and it's negative. As x increases, y gets smaller. At this point, the slope is 0. Over here, kind of by symmetry, the slope will be plus 1.7 over 6, and so on. So if I do that, let's do a couple points. I chose minus 1.6, minus 0.8, 0, 0.8, plus 1.6. At each point, you draw the derivative and then find the slope. The slope is change in y over change in x. So here the slope is minus 3.2. Here the slope is minus 1.6. Slope is 0, plus 1.6, plus 3.2. So that's the slope at a couple points. What I could do then is connect the points. So here's the slope at minus 1.6, minus 0.8, 0, plus 0.8, plus 1.6. Connect them with a curve, and that is the derivative of the parabola. So that's one way to find a derivative. Just draw the tangent at a bunch of points and then connect the lines, connect the points. That's a graphical method. And when you take calculus, you're going to learn that the derivative of x squared is 2x. And that's kind of what we're seeing here. This is a straight line, passes through the origin, and the slope of the line is 2. As you go to the right by 1, I go up 2. Let's take another function. Let's find the derivative of sine of x using graphical methods. So here the blue curve is sine of x. Where it's flat, the derivative is 0. So I can mark these points. At this point, the slope's the maximum. So if I look at the slope, I go right 1, draw the tangent, I go up 1. So here the slope is plus 1. Over here, the slope is minus 1. I go down 1, draw the tangent, go over 1. So here the slope is minus 1. Draw a curve between them. And that'll be the derivative of sine. And what that looks like is this. The blue curve is sine of x. This is the derivative. And it turns out this is actually cosine of x. The derivative of sine of x is cosine of x, found using graphical methods. Third example. Find the derivative of cosine of x over x squared plus 1. Now this is one, if you've had calculus 1, it's still kind of hard to find. But using graphical method, it's not too bad. What I would do is where it's flat, the derivative is 0. And let's change the color. Trying to change the color here. So here the derivative is 0. Right here where it's flat, the derivative is 0. Flat, derivative is 0. Flat, derivative is 0. So that's where the derivative is 0. Right here looks like the maximum slope. The slope, see from here to here, the change in x is 0.5, change in y is 0.7. So it looks like 1.4 negative. So 1.4 about here. At this point, kind of my symmetry will be plus 1.4. Right here, the slope is, so here's 1 for x. Change in y is 0.2, 0.4, about plus 0.4. So it's kind of doing this. It goes negative, 0 crossing, plus 0.4. That's what the derivative looks like. Again, pick a bunch of points, find the slope at those points, and then connect them. Blue is my function, the red curve is my derivative. So that's a couple ways to find the derivative. A third approach is using Matlab. Not too surprisingly, since this is a Matlab course, I can use Matlab to find derivatives. And I'm going to find it using numerical methods. So suppose I have a function y of x. I've got a bunch of different points for x. I've got a bunch of different points for y. The derivative at a point, say at y of 4, is the slope. Roughly the slope is change in y over change in x. So take the point 1 after and before, y of 5 and 3. The change in y is y of 5 minus y of 3. Change in x is 5 minus 3, 2. So the slope is dy over dx, y of 5 minus y of 3 over x of 5 minus x of 3. That's a numerical way to find the derivative, and it's not exact. But as the spacing gets tighter and tighter, it gets more and more accurate. So with that, I have an algorithm to find the derivative. The derivative using numerical methods would be if I have a whole bunch of points for my data. Say here's my curve. There's x, there's y, there's the first point, second point, third point, fourth point. At any given point, like point I, take y of I plus 1 minus y of I minus 1 over x of I plus 1 minus x of I minus 1. That's roughly the derivative at point I. Now note when you do this, it works for all points, and that kind of implies a floor function for I equals 2 to n minus 1. I've got a problem with the two endpoints. At the first endpoint, there is no point to the left. At the last endpoint, there is no point to the right. So that's typical with numerical differentiation. The two endpoints, they have to do something different. What I could do is at the left endpoint, just take the second point versus the first point, change in y over change of x. At the right endpoint, find the change of y over change of x. Not quite as accurate, but again, I don't have a whole lot of choice in the matter. That leads to a function in Matlab. Let's create a function called derivative. I'm going to pass to it some data, and it will return the derivative. So I'll go into Matlab and do new function. I'll then type this into Matlab. My function is called derivative. I'm going to pass my data points x and y and return the derivative, dy dx. This should really be dy over dx, except that that's not really a valid Matlab variable. So I'm just going to call it dy, the derivative of y. And when I calculate it, I'll return dy. So let's start out. NPT is how many points are in my functions, x versus y. Let's have dy have the same dimensions as y, or x, starting at zeros. Now as I go through my data, I'm going to skip the first endpoint and go from data point number 2 to n minus 1. At all these data points is the algorithm that we had before. The derivative at point I is the change in y for the point after and before, divided by change in x for the point after and point before. Now fix the two endpoints. The first endpoint is roughly, again, since I don't have a point to the left of the left endpoint, change in y over change of x on the left side, change in y over change of x on the right side. There's my function. Now save it. If I save it as derivative.m, I can now call it. And anytime you write a new program, it's good to check your function. So from Math 165, if you've had it, if not, just take my word for it. The derivative of 2 sine of 3t is 6 cosine 3t. I know what the derivative of 2 sine 3t is. Let's check to make sure that my function gives the same answer. So let's have x go between 0 and 4, steps at point 1. Y is sine of 2 is 2 sine of 3x. Now calculate the derivative. I'm going to pass x, pass y, and calculate the derivative of y. I'll then plot x versus the calculated derivative in blue. So here blue is calculated. X versus 6 cosine of 3x. That's the right answer in red. So here the red line is the correct answer. The blue dots are my calculated answers. And the two match up pretty well. The endpoints are a little bit off. That's not atypical with numerical methods. But the other points are dead on. So I'm fairly confident that my function derivative is working. Let's take another example. Let's take y is e to the minus x squared cosine of x cubed. Find the derivative. Well, even if you've had calculus 1, this is kind of a tough one to solve. That's the beauty of numerical methods. Once I get my function derivative, I don't really care whether I can do it by hand or not. It's the same algorithm. So let's find this using numerical methods. Let's have x go between minus 4 and plus 4, steps of 0.04. Y is e to the minus x squared cosine of x cubed. Plot x versus y. And so this is your function y. Now take the derivative. Find the derivative of xy. Again, Matlab doesn't care what these are. Given some data, it'll find the derivative and plot x versus y in blue, x versus dy in red. So this is the derivative. For notation, y prime means derivative. That's sometimes used just because dy over dx is kind of a pain to write. So here's the derivative. And if you check it, it kind of makes sense. When y is flat, the derivative is 0. When y is flat, the derivative is 0. The y is increasing, derivative is positive. Y is decreasing, derivative is negative. The red line is the derivative of y. And that's kind of neat. That's one of the beauties of Matlab. If I can get the data into Matlab, I can find the derivative. This is also useful when you take Math 165. I can calculate the derivative and then check with numerical methods. The numerical method will tell you what the data should look like. If I analyze this by hand, I'll get the equation for the derivative. The two should match up. Some of the uses of Matlab, or some of the uses of derivatives. If you notice, when I'm at a maximum, the derivative is 0. When I'm at a minimum, the derivative is 0. That's the method you're going to use when you take calculus to find the derivative or to find the maximum or minimum of a function. I take the derivative and set it equal to 0. The zero crossings of the derivative are where your function's a maximum or a minimum. So that's kind of the idea behind derivatives. There is a problem with derivatives. Typically when people take Calc 1, Calc 2, you have differentiation, integration. Integration we'll cover next week. Students tend to like differentiation more than integration because differentiation is just apply a set of rules and you can memorize those rules. In practice, differentiation is not ideal. Differentiation is really bad when there's noise. Typically when you have real data, there's always noise in it, like it's jittering up and down. When I take the derivative, that amplifies the noise. For example, from 2 weeks ago, this is the Arctic sea ice versus year. If I take the derivative of that function, here's what it looks like. So here's your y, here's y prime. What the derivative would tell me is how much sea ice I'm losing each year if it's negative, how much sea ice I'm gaining each year if it's positive. Because of the yearly fluctuations, that's the noise, when I take the derivative, pretty much all I see is noise. It actually is negative. There's more points below 0 than above 0. But because of all the noise, it's really hard to tell what's happening. That's very typical with derivatives. If there's any noise in the data, the derivative amplifies the noise. Another example. Here's global temperatures. If you look at it, it's pretty clear temperatures are increasing. That means the derivative, or the slope, should be positive. There is yearly fluctuation. That's your noise. If I take the derivative, and here's y prime, all I see pretty much is noise. That's a real problem with derivatives in practice. Derivatives tend to be noise amplifiers. So that's kind of what a derivative is. And with Matlab, I can find the derivative using numerical methods. Even if I can't find it by hand, as long as I get the function into Matlab, I can find the derivative. Here's an application of that. It's in robotics for path planning. Suppose I have a robot arm going from point A to point B. How do I do that? If I plot it versus time, so here's time, here's your angle. If I start out right here at point A, I wind up at point B. There's a couple ways of doing it. I could do it this way, I could do it this way, that way. Many different paths I could follow. That's called path planning. How do I analyze those paths? Which one's better? Well, one way to do that is to use the derivative. The angle is just the angle. The first derivative is the velocity of the motor. For DC motors, velocity is roughly voltage. The second derivative is acceleration. For DC motors, acceleration is basically current. So by looking at the first and second derivative, I can see what voltages I need to apply to the motors and what current I need to apply. So, suppose just for fun, I want to go from point A to point B and assume A is equal to 0, B is equal to 1. And I want to get there in 2 seconds. What ways can I do it? One approach is to just have a straight line. The nice thing about a straight line, it's pretty simple. The problem is I have these jump discontinuities, and I'll see that when I take the derivative. So this is what the function y looks like. It's 0 for time less than 0, 1 for time bigger than 2, and the slope of the line is change in y over change in x is equal to 1/2 in the middle. So let's take the derivative. If I take the derivative, so here's my time. Time goes from -3 or -1 second to +3 seconds. Y, the blue line, is 0 for t less than 0. It's t over 2 for t greater than 0 and t less than 2. And it's 1 for t greater than 2. So kind of what I did is I split this up into 3 different regions. In this region, region A, it's equal to 0. In this region, region B, it's t over 2, and that's true for t bigger than 0 and less than 2. And region C, it's 1. That's y. Once I get y into Matlab, I can find the derivative. dy is the derivative of t and y. The second derivative is the derivative of the first derivative. If I then plot it, here's what the plot looks like. So y is kind of a nice function. It goes from 0 to 1, just like I expect. The first derivative is 0, then it jumps up to 0.5, and it jumps down to 0. That's the voltage that I apply to the motor. I have this jump discontinuity, which isn't a big deal. That's like you turn on the light switch. If I take the second derivative, that's the derivative of the red line. It's 0, jumps to infinity, goes back down to 0, jumps to minus infinity, goes back down to 0. That's the second derivative. That infinity is kind of a problem. This means that the current is 0, then I get this big bang of current, gets the motor moving, then I get a big bang of current, getting the motor to stop. Infinite current is kind of hard to achieve. That tends to saturate the power supplies, burn out the windings. That kind of says this is actually a pretty bad path, and I can see that in the second derivative. Okay, so let's come up with a different path. I want to go from 0 to 1. There's point A, point B, in 2 seconds. One way to do that is make this a cosine function. So this is equal to, and cosine goes 0 to 1. Let's do 1 minus cosine. At t equals 0, 1 minus 1 is 0. At this point right here, I want to be the peak. At t equals 2, I get cosine of pi. Cosine of pi is minus 1. 1 minus 1, 1 minus minus 1 is plus 2, divided by 2. So this is a cosine function. Kind of what that looks like is it's a minus cosine that looks like this. Offset by a half. There's the plus 1/2. With the negative, normally cosine is a peak. At t equals 0 and goes down. There's the minus. Net result, there's your function. And then for t greater than 2, it's equal to 1. So that's a little bit more complicated of a function, but the nice thing about it is when I take the derivative, I don't get these jump discontinuities, and I can see that in Matlab. I'll input the function into Matlab. T goes from -1 to 3, steps of 0.01, plus 10 to the minus 6. I did that just to avoid 0 over 0, and I don't have to worry about the greater than or equal to. This is never actually equal to 0 or equal to 2. Just perturb it just by hair. Y then is 0. This is region A. For t less than 0, between 0 and 2, region B, it's 1 minus cosine pi times t over 2 over 2. There's region B. And region C is equal to 1. So this is valid between 0 and 2. This is valid for time greater than 2. Given t and y, find the derivative. Given t and dy, find the second derivative and plot them. And here's what you have. So here's y, the angle. The derivative is the red line. Initially, the derivative is 0, becomes maximum, goes back down to 0, and stops. The second derivative is the purple line. The derivative of the red line is 0, jump discontinuity, becomes positive. Here's the peak, 0 crossing, becomes negative, jump discontinuity. That's a much more reasonable path. The voltage to the motor goes from 0, becomes a maximum, goes back down to 0. The current to the motor has a jump discontinuity. Again, not a big deal. That's like you turn on a light switch, current suddenly jumps up, goes negative, then turns off. So that's actually a much better path. That's kind of the idea behind path planning in robotics. How do I go from point A to point B while keeping the voltages and currents reasonable? And a cosine is one way to do it. There are other paths. What I could do is I could keep the acceleration constant. So if this is y double prime, that implies a different path. I could say I want to start with 0 acceleration at the beginning and end. I could say I want the acceleration to do this. So this is y double prime. Find y prime and y. I could do a cubic function for y. Many different ideas. And that's kind of the idea behind path planning. It's what's the best path for going from point A to point B, and to evaluate them, I use derivatives. So kind of in summary, derivatives and differentiation are useful. If you look at your bank account, the derivative tells you how much money you're adding or how much money you're depositing. If you look at Arctic sea ice, the derivative tells you how much sea ice is being added or how much is being lost. If you look at DC motors, the first derivative is the voltage to a DC motor. The second derivative is current. To find derivatives, I can use tables and memorization. That's what you do in Math 165. I can use graphical methods, where the derivative is the slope, and I can use numeric methods. The nice thing about numeric methods is that something you can program into Matlab, create a function to find the derivative, and once I get that function, as long as I get the data into Matlab, I can find the derivative. There is a problem, however. When you differentiate, I tend to amplify noise. So if you have really clean data, I can find the derivative. If there's any noise in the data, it tends to be a noise amplifier. So with that, you should be able to do the homework set for week number 6, finding the derivative using graphical methods and numeric methods. For finding the derivatives by hand, stay tuned until you take Math 165. And that's lecture number 6 for ECE 111.